Okay, so we are starting review for chapter C. I think this is the most important chapter and it provides the base for the whole course. Okay, so this is a very important chapter. Um, so this chapter relates with finding the thermodynamic properties for pure substance. Okay, so I hope you already know what pure substance is by now. Um, See now why this chapter is important. So our goal is to find the properties, right? So that's what we want to find. The important question is why do you need to know the property? So our main goal is to make use of laws of thermodynamics. And if you think about the first law of thermodynamics, you could see like the variables like internal energy. You could see the variable like enthalpy. You see the variable like specific volume. So these property must be known to solve the energy equation, right? So without knowing the value of property, you can solve this energy equation. So how do you get these values? So that's the point. So that's what we are trying to figure out. So there are different ways by which we can find the property. Like you could use the formula. That is one way. The other way could be um, a chart. So this is a chart or graph, and the big one is the property table. So these are the three ways by which you can find these property values so that you can solve the energy equation. I think the formula for simple case is, you can use still for simple case you can use the formula, but most of the time the formula are very complex and not a good way. So it has certain partial derivative, and for solving the problem, it's not that easy to carry out partial derivative every time. Chart. So this is another option, but it doesn't give you the exact value. Okay, so it has certain limitation. So in some cases, we learn how you can use the chart to solve the problem or to find the property. The third option is the property table, which is the most accurate one. Is the most accurate one. And our focus should be mostly on figuring out how we can find the property using the property table. It has also certain limitation, like it is bulky and so much of data to look at it. So it has certain limitation as well. But I think it gives you a very accurate value of the property using the property table. So that's the reason why, again, the goal is, the big picture is we want to apply the laws of thermodynamics. And in order to apply the laws of thermodynamics, you could see here, if you think about the first law of thermodynamics, we need to know the value of property. The property could be internal energy, it could be enthalpy, it could be specific volume. So this value needs to be known. So how do you find those values? And these are the three possible ways, and the most reliable and the most accurate method is using the property table, and that's what this chapter is focused on. Okay, that's the motivation of this chapter. So when you are trying to find the property, it's always important, like what substance, because if it is a steam or water, okay, it's steam or water. Steam doesn't mean that it's always vapor. Okay, I told in the class as well, it could be saturated liquid, saturated vapor, mixture of saturated liquid and vapor, or it could be superheated, it could be anything. So don't get confused with the word steam. If it is R134, you need to look the different table. If it is nitrogen, you need to look at different table. So depending on what substance, so always try to highlight the keywords, and very important keyword is the substance. Figure out which substance it is, and based on that you have to use the property table. Next is you need to figure out what system of unit um, you are going to use. So whenever you read the problem, it gives you a hint which type of system you have to use. Don't try to use two system of unit. Just either stick to SI unit system or you stick to English unit system. So don't get mixed up. And from exam point of view, I will not be asking question that would be kind of mix up. It would be either everything in SI unit system, but again, remember, it's important to convert to the basic unit as you solve the problem. And the other thing is like if you think about steam, sometimes it may not tell you, is it saturated vapor or is it a superheated or subcooled? It doesn't tell you, so you need to figure out, right? So it could be that kind of substance. So for steam and refrigeration, you have different phases. If that is the case, you need to figure out where it lies, whether it's a subcooled or it is a saturated mixture or it is superheated, and then find the property accordingly. In some of the cases, for instance, if it is nitrogen, I don't think we talk about phase change, right? Carbon dioxide, it's always, this is gas, right? It's in gas. In thermodynamics, we most of the time, like air, nitrogen, carbon dioxide, then it just exists in one phase, so which is gas. So you don't have to worry about um, saturated mixture, liquid and vapor, or the soft cooled, because we know for this gas it just exists in uh, one phase. So you'll find the table of this property, but you won't have for like saturated mixture or the soft cooled. So you need to understand that when you see substance which are in superheated or the gas like air, nitrogen, carbon dioxide, you can still find the property, but you will not get the table for soft cooled or saturated mixture. So you just have to keep that in mind. Okay, so the overall concept map for this chapter is, again, our goal is to find the property, and is to find the property of a substance, because we want to solve the thermodynamic equations. So we need to find the property, as we just discussed before. So your thought process is, again, whenever you read the problem, try to figure out what substance it is. Is it H2O, water, steam, or is it R134A, which is a refrigerant? Is it nitrogen? It is oxygen? Based on that, always highlight the keyword, the substance, and then and figure out which table we need to use. Next is, so let's say we are using the substance is water, or it could be steam, it's the same thing. Next is, you need to verify which system of unit you are using. So you have two options. If you see in the appendix property table, you have SI unit system, and you have appendix 2, which is English unit system. Now if it is a pure substance we change phase, then we need to figure out whether it is a subcooled or it is a saturated or it is superheated. If it is subcooled for water, it is A7, appendix A7. If it is a superheated, it is A6. Again, we are only focused on water. See, this is very important. And then you can find the property from the property table. For superheated, there are other ways by which you can find the property. We'll discuss about this in later on. Again, like if you have gases like hydrogen, oxygen, nitrogen, then you can use the ideal gas equation or ideal gas equation with the compressibility chart. So these are the possibility which you have. So these are like handy equation where you can find the property. If you know two property, we can find the third property. So this is important for gas. So you can't use this for, remember, the ideal gas equation and ideal gas equation with the compressibility chart you cannot use for liquid, or you cannot use for solid, or even a mixture of liquid and vapor. It has to be completely gas or superheated vapor, and we'll try to figure out the situation in which ideal gas equation gives you good results, and in which case the ideal gas equation does not give you a good result. Again, coming back to for the substance where phase change occur, the saturated one, and again you'll find that for saturated you can have pressure based table. So if the pressure is given, then you have to use the pressure based table, which is A5, and if the temperature is given in the problem, you have to use the temperature based table, which is A4. And when it is saturated, you have three options. It could be saturated liquid, it could be saturated vapor, like here. So this is a saturated liquid, this is all saturated vapor, and then in between you have a mixture of saturated liquid and saturated vapor. Okay, so this is kind of overall picture. So I just showed this for water, and then SI unit system. You could do the same thing for um, in English unit system, and there is an appendix um, where it gives you the property value uh, in appendix 2. Okay, so this is for water. You could do exactly the same thing. I did not show in detail, but you could do the same thing for a refrigerant. I think in the appendix it gives you the property value for one R134A, which is a refrigerant. Again, for this refrigerant, the phase change takes place. So you have, even for R134A, you see subcooled, you see saturated mixture, you see superheated. So figuring out where it lies and how you find the property is the most important thing. So this is for refrigerant, and you'll also find the property for maybe nitrogen, oxygen, carbon dioxide. So in this case, we don't talk about phase change because we assume these are all gases. So you'll see the property for these gases. So you won't get for nitrogen, you will not have like subcooled nitrogen or a saturated mixture. So only for gas phase or superheated. So you'll find the table for other substance as well in the appendix. For the substance where there is a change in phase, you have three cases. One is in the problem, you need to see if both P and T, pressure and temperature, is given. This is one option, and you need to find all other property. Okay, so and if you pressure and temperature is given, by using the property table, you can find all other property. The key is you have to compare this. In order to figure out where it lies, you need to compare with the P saturation and T saturation, and based on that you will know where it lies. Case 2 is not both the pressure and temperature is given, but either pressure or temperature is given, and any property would be given. So if that is the case, you need to compare this with subscript F, the property value at that pressure or temperature, and then subscript G. And based on that, you'll find whether it's a superheated or it's a subcool or it is a saturated mixture. You can make a decision accordingly based on this one. And case 3 is when the value of quality is very important. Quality is mass of vapor divided by the total mass. So this is the saturated mixture region. So if you think about this one, saturated liquid, the quality is x equals to 0, and for saturated vapor, x equals to 1. So it talks about this whole region. So the quality value is irrelevant in the subcooled region, and also is irrelevant in this superheated region. The quality value is only relevant in the region between saturated liquid and saturated vapor, and saturated liquid has quality of 0 and the saturated vapor has a quality of 1 depending on where it lies. So in the middle it would be quality would be 0.5 and so on. So if the quality value is given, if you do not know the value of quality, if you know it's in the saturated mixture region, if you do not know the value of quality, you won't be able to solve the problem. So the most important variable is the quality if it lies in the saturated region. Okay, that's the most important quality. You need to figure out the way by which you can find the quality. Once you know the value of quality, then you can find any property. Again, our goal is to find the property, and later on, once you find the property, you can use in the thermodynamic equation to solve the unknown. So that's the main motive of this chapter. Okay, so this I think we did this exactly the same problem in the class. So this is the table. You need to kind of fill in the blanks, all these. So use try to figure out your thought process, try to figure out which case is it, which case 1, case 2, or case 3, and then you need to show the detailed work. It's very important to show the detailed work whenever you solve the problem. Only writing the answer is not enough. So whenever I grade from exam perspective, if you show all the detail, even and the answer is wrong, but if you follow the right process, you still get good score. So it's very important you show the detailed work whenever you are solving the problem. So you need to fill in the blanks, and you just have to do the same thought process. Which substance is there, whether you are using SI unit or English unit system, where does it lie, is it a saturated liquid or superheated or saturated mixture, and then which case is that, case 1, case 2, and case 3. And once you identify where it lies, then find the property from the property table. So that would be the thought process in solving these kind of problem. And this is very important. This is going to be very important moving forward. You will see here, determine the missing property of the phase description in the following table. See, this is water or steam. So this is what is given. So this is, we know now, we need to look for the in the appendix for the water. And then so we know water now. What system of units? So it's given in centigrade, kilopascal, and kilojoule per kg. That means you are using SI unit of system. Okay, so now you need to next is, once you know this, we decided it's water, it is SI unit of system. Now for each case A, B, C, D, E, you need to find out which case is it. And then once you know which case, then use this condition to figure out where it lies. And once you know where it lies, use the particular table to find the property. So for instance here, for A, pressure is given 200 kilopascal, and the quality value X is given 0.6. So which case is this? When quality is given is the case 3. If quality is given, so this is given, pressure is given, so you can look at the pressure table. And then once you know that, you have enough to find the internal energy. So if you try to look like this, so this is a TB diagram. So the quality is 0.6, maybe, so somewhere here. And remember, in the saturated mixture region, pressure and temperature are dependent. That means if you know the pressure, we know the temperature. So at that 200 kilopascal, so this is the table, which is I think for water it is A5. You need to look at the table. And then at this table, because pressure and temperature are related, so you can find out how much is T saturation. So this will give you the T saturation. And for finding the internal energy, the quality value is already given. So at this pressure, you can find out how much is UF, how much is UG, and UFG is UG minus UF. Okay, and you need to find the property value. So U would be UF plus X UFG. So X is 0.6, you get from the table, from the pressure based table, so you know everything. So that's how you need to do the calculation for A. Okay, so that's what is shown here. That's what it is shown here. Okay, so this is what is shown here. So you know UF and UG and T saturation and everything. And so it is in a saturated vapor mixture. So this is the formula which you need to use and find the property value. The second question is B is temperature is given, and then one of the properties given. So this is a case 2, pressure or temperature, any property is given. So if that is the case, then your thought process is you need to compare with UF and UG and find where it lies. Okay, and where it lies. Once you know where it lies, then go from there. So so the temperature is given, so you need to look at the temperature table. You need to find and then U is given. So at this temperature, find out how much is UF and how much is UZ. You can find from the table. So these are the UF and UG value you get from the table at 125 degrees centigrade, and then compare where it lies. So you know, again, this comes handy. If U is greater than UZ, then this is superheated. If U is less than UZ, it's subcooled. And if it lies in between, U has to be between UF and UG. And you can see here, U lies between UF and UG. That means it is a saturated mixture. Now, the most important variable in saturated mixture is quality value. Without knowing this, you won't be able to solve the problem. So you need to find the value of quality. Okay, so I think in the table this is kind of unknown. So U is given, UF, UG is known, UFG is known. So the quality value is you can get from this equation. Since it is in a saturated mixture region, if you know pressure, we know the temperature, and if you know temperature, we know the pressure. So for this temperature 125, this is the saturation pressure. See, so we know in the saturated mixture region, pressure and temperature are related. Okay. Third question is very similar to the previous questions, where pressure is given instead of temperature. Pressure is given, one property pressure is given, and then another property which is internal energy given. So this is a case 2. Again, for this one you need to compare this is UF and UG and try to find where it lies. So if you see, you can see that um, the value of U is greater than UG, so it lies in the superheated region. Now you need to, next step is to look at the property at the superheated region. You need to be careful with the unit. See here, see it is in megapascal, so you have to convert that pressure to a megapascal. So you should know this conversion, okay? But the thing is, we need to find the temperature. So at 100 kilopascal, which is 1 megapascal, uh, the value of U lies between these two temperatures, so the exact value is not given. So you should know how to do the interpolation. So you will come across many problem where you need to do the interpolation. Okay, so in order to find the temperature corresponding to this U value, you have to do the interpolation, and I hope you know how to do the interpolations we discussed in the class as well. So this is your answer. For D, pressure and temperature given. So for this, compared with the saturation temperature and saturation pressure, you could do either of it and then find out where it lies. Okay, and you could see here, you don't have to do both. You could do either of this, and you find like both would give you the same result, and it's in the subcooled region. And for subcooled region, there are two ways finding the property. The one way is very simple way where we do most of the time is U at subcooled region is UF at that temperature. So in the subcooled region, the property are function of temperature. So at any point, if you want to find the property, like somewhere here is the property value at saturated liquid region at that particular temperature. That's how you find the property. This is one way. The other way is you can use the subcooled property table, which is I think A7, and most of the time uh, you may not get the property value for all the range of pressure and temperature. So that is why this another way of finding the property for subcooled region becomes handy. Okay, so you could do for any property. So enthalpy is HF at that temperature. See, temperature is a function of, this is important, not, you should not look at pressure table to find this property for subcooled region. You should look at the temperature based table, because in the subcooled region the property are function of temperature. Okay, so this is very handy if you want to find the property in the subcooled region. Okay, that's what I have done. U is UF at that temperature. See, here is temperature, not pressure. So that's how you find the property. Again, the last case here, the quality value is given, so which is x equals to 0, which is a saturated liquid, and then pressure is given, so it's very easy. The property would be UF, right? UF, and then since in the saturated region, pressure and temperature are related, so at this pressure, find out how much is desaturation, and that gives you the value. Okay, so this is how you have to solve the problem, and this concept is very, very important. Okay, so you should know how to do interpolation, because when you are solving this kind of problem, the value in the table may not be given exactly at whatever the temperature or pressure. Like for instance here, we have enough to find the enthalpy at 72 degrees centigrade, and if you look at the table, uh, see, you have at 70 and you have at 75. You don't know what is at 72. So if that is the kind of situation, you have to do interpolation. You need to find the value in between what is known. So that is called interpolation. So it is same as saying uh, uh, you are given, the coordinate x1 y1 is given, and x2 y2 is given, and then you want to find in between this x y. So in this, either x is given or y is given, so it doesn't matter. So you can find when x is given and then y is known, or when x is given and then you find y. It has to be just one unknown. So so you can use this formula whatever the way you want. So it is, if you write in terms of y and x, it is y2 minus y1, x2 minus x1 is y. So this is the formula which you can use it to solve the problem. Okay, this whatever we discuss is about a substance which changes phase, but there may be a substance, just gas, or if it is in superheated state, you can uh, solve this type of problem, which are handy using either ideal gas equation or ideal gas equation with a compressibility factor, or the one which is a property table. So these are the three possibility, and we already know how to find the property for a superheated vapor, or gas means it just exists in one phase, remember. So you don't if it is a gas like nitrogen, don't try to look where does it lie. You don't have to look for that, because you already know it's all just gas. Okay, so it's like superheated. So that's important to understand. A property table is, it's good, but it's kind of bulky, so that's kind of limitation. Ideal gas equation is the least accurate and easiest way to find the unknown. So the equation is ideal gas equation, PV is equals to RT. Very simple equation, but in some cases it does not give you the good result. In order to compensate for that, we have ideal gas equation with a compressibility chart. So this ideal gas equation would turn into PV equals to ZRT. So this compressibility factor, how do you find that value, become question that we are interested in. Okay, very important, never use ideal gas equation for liquid, or for a mixture of liquid and gas. This ideal gas equation and compressive factor only can be used for gas state. Okay, remember, this is very important. I have seen in the past it says liquid or saturated liquid and vapor, and you are using ideal gas equation. That is absolutely wrong. This equation holds true only for gas. That is very important. That's what I have written here in note. Ideal gas equation and compressive factor should be never be used for solid or liquid vapor mixture. It can only be used for gases. This is a very important statement. And you see in the problem, if it's not gas or if it's changing phase, then don't use ideal gas equation or ideal gas equation with the compressibility factor. Again, this is for superheated or gas, you could do using the property table, or you can use ideal gas equation or ideal gas equation with the compressibility chart. So these are the options which you have. So so it could be some gases or superheated vapor in which we can use this ideal gas equation or ideal gas equation with the compressibility chart. Okay, so let's try to the ideal gas equation. It looks very simple. PV, it's important to know what each variable mean, and most of the time where you make mistake is the unit system. So my recommendation whenever you are using ideal gas equation is to convert all the variable to the basic unit. So if you are doing in SI unit system, pressure convert to Newton per meter square. This is specific volume, it is in meter cube per kg. And this temperature, very important, it has to be in absolute temperature scale. So if it's in SI, it has to be in Kelvin. If it's in English unit system, it has to be in Rankine. Okay, and this R is a gas constant depending on what gas you have, and this value can be found from the appendix A1. So you should be ready to use appendix A1 for this type of calculation. Depending on, so you need to look for which gas it is, and based on that you need to find the value. And then also you need to be careful regarding this unit. Okay, I think the unit is in kilojoule per kg per Kelvin, so you need to convert kilojoule to joule. So the basic unit again, joule per kg per Kelvin. If you do that, you don't have to worry about the unit. Okay, and this gas constant is related with universal gas constant. by this. So this is universal gas constant whose values are constant. See, these are given in different unit, and m is the molecular weight uh, of a substance. Okay, so this is very important that whenever you are solving the problem, you must know what each variable mean and what are the units of each variable in basic unit, so you don't have to worry about the cancellation of the units. That is extremely important, and that's where you tend to make mistake if you do not follow the proper unit conversion. Okay, um the basic formula for ideal gas is pv equals to rt. So this is specific volume. Specific volume is volume per unit mass, so you can also write PV, which is volume, and then you can have like mass. This is mass RT, and mass can be molar mass multiplied by the number of mole. This is another way of finding. So sometimes you may have to use this equation if you, and if you are using in terms of number of moles. Here this is universal gas constant. So these are all the ideal gas equation in different form. And sometimes if you see the bar on the top of this, it is always in terms of molar mass. It could be kilomole. See, this is a per unit mass, this is V, and V bar is per unit molar mass, kilomole. So you have to understand what that bar means uh, in terms of the unit. And now, when can you use this equation? This is very, because as the name suggests, ideal gas. What is ideal gas? These are just a hypothetical gas, right? So this equation can only be used when pressure is low and then temperature is high. So when you have a low pressure and high temperature, the ideal gas equation still gives you good result. Okay, good result. So this is a situation in which this low pressure and high temperature. Okay, so in this area ideal gas can be used. So this point is a critical point, and near this side, this ideal gas does not give you a good result. Okay, so in order to compensate for that, that's why you have ideal gas equation with a compressibility chart in which you have this equation. Now PV is GRT. Okay, so this is a value which we are interested in. If you know that, we can solve this equation. So for that we have to see these plots are used. So I think it's A15. That's what you need to bring. You only provided with this plot, but I'm just trying to show an expanded view. The y-axis is G, and then x-axis is reduced pressure, and reduced pressure is P by P critical, and P critical is the pressure at this critical point. Okay, so the critical point is where the saturated liquid line and saturated vapor line intersect. So that's what the critical pressure line critical point is, and the value of this can be again find from the A1. So this for appendix 1 you can find that. So is the case for T critical, and VR is obtained from, if you know, because P and V are related, right? So you can find from the T critical and pre critical, you can find how much is volume, reduced volume. Okay, so reduced volume can be found using this. So reduced pressure is P by pre critical, reduced temperature is T by T critical, and for reduced volume you have to use this formula to find the reduced volume. And you see in this plot, x-axis reduced pressure. So if you know reduced pressure and these are reduced temperature, so if the reduced temperature is 1 and then maybe reduced pressure is 3.5, so this is the 1, so this is 1, and then corresponding to this you can find the value of G. So once you know the value of G, substitute in the equation and then solve the problem. Again, I would like to emphasize that solving PV equals to GRT, the key is finding G, and I showed you how you can find. Now let's try to see this problem which involves ideal gas equation. Okay, let's start with the ideal gas equation. So here determine the specific volume of superheated vapor. See, it is a superheated vapor. And by using, and it already tells you, if you do not know it's a superheated vapor, you can never use the ideal gas equation. If it was gas, then you could use the ideal gas equation. So since superheated vapor at 3.5 megapascal, so this is the pressure and temperature is given, you need to find the specific volume using the ideal gas equation. So for this type of problem, again, the key is knowing what variable is in the equation and what are the basic unit. So here we are trying to solve using trying to solve the problem using SI unit system. So if that is the case, pressure has to be Newton per meter square, temperature has to be in Kelvin, specific volume it would give you in meter cube per kg, and R has to be joule per kg per Kelvin. So once you know that, then just convert to it. So here it's given in 3.5 megapascal. So 3.5 multiplied by 10 to the power 6. So this is in Pascal, or Newton per meter square is the same thing. The temperature has to be always absolute. So in SI unit, it has to be in Kelvin. So you'd add 273. Now this is the equation. P is given, T is given, specific volume you need to calculate, and R. Now you need to find the value of R again. This is a gas constant, and you get from appendix A1. Now where you need to look? You need to look, is a superheated water. It's a water, so you need to find where water is. Water is here. See, you see the critical properties are given, and also the R, gas constant. So this is given 0.4615. So this is given this one. Remember, see, always be careful with the units. So you have in kilojoules. So convert these to joules. So just multiplied by 1000 kilo. So this gives you in joule per kg per Kelvin, which is a basic unit. Okay, very important. So this where you tend to make mistake. So everything in basic unit, pressure in Newton per meter square, this in joule per kg per Kelvin, and then the temperature in absolute temperature scale, which is in Kelvin. Now this should give you answer in meter cube per kg. So that's how you solve the problem in ideal gas equation. The second is, you maybe have to do using the generalized compressivity chart. So there are three options. I think we discussed in the class as well. The pressure and temperature is given, and find the specific volume, like in this problem. So this is the procedure which you need to follow. Find the reduced pressure, find the reduced temperature, and then find G from the A15 that you need to bring, appendix 15 plot that you need to bring for the exam. And then from there you can find, once you find the G, you can find the unknown specific volume. Sometimes pressure and volume is given, you need to find the temperature. So in that case, so this is the formula for PR, this is the formula for BR. See, the critical temperature and critical pressure you can find from the appendix 1. Again, careful about the units. R value, again, careful about the units, you can find from appendix 1. And for known PR and VR, from using the table, using the chart, you can find TR, and we know T is TR, T critical. So you got from the figure T critical from appendix A1, so you can find the temperature. So is the case when the T and V is given, you can find the pressure accordingly. So these are the steps which you need to follow depending on what is given and what needs to be found out. So this is what you can bring in the exam. If you see the difference between these two plots, the only difference being here is, so you see here is from 0 to 7, and this is kind of expanded view of this 0 to 1, only this. So this is expanded here. So if the value of PR is in this range, you better use this one. And you see these are TR plots, so these are TR, and also you could see these are the lines which are for VR. So sometimes you may have to use VR as well. So from exam point of view, you may not get, you are just trying to visualize, so you may not get exact value, but if you get close to that and show the process is still okay. You don't have to worry about if there is deviation in terms of actual answer when you are solving the problem. Okay, so this is appendix 1, very handy, which gives you the value of gas constant depending on what gas you have, and also the critical property are required. So this is for the temperature in Kelvin. Again, be careful about the unit. Pressure is given in megapascal. Okay, so whenever you are trying to find out reduced pressure, P by P critical, make sure both are in the same unit. And for temperature, very important, when you are finding temperature, reduced temperature, it has to be always in absolute temperature scale. Okay, if you are using an SI unit, both this temperature has to be in Kelvin, no Celsius. Even though it seems like Celsius and Celsius cancel out, but that is absolutely wrong. It has to be, if you are using SI unit, both has to be in Kelvin. If you are using US English unit or US customer unit, both the temperature has to be um, in Rankine. Very important. So whenever you are using ideal gas equation or ideal gas equation with the compressibility chart, make sure temperature are always in absolute temperature scale. Don't have the temperature either in Celsius or Fahrenheit. You won't get the right answer. It's a very important thing to consider when you are solving the problem using ideal gas equation or ideal gas equation with the compressibility chart. Okay. I think that's it. Like that's what I was discussing about using. So in this problem, the pressure and temperature given, you have to find a specific volume using the compressibility chart. So in that case, is the case 1. So you need to find the value of G. So using the table, find these value, and P and T is given. You can find out PR and TR. So this PR is given. PR is given found from here. TR is found from here. So once you know this, wherever it lies, then y-axis give you the value of Z, and you can use the ideal gas equation with the compressibility chart to find the unknown. Okay, so this is how you solve the problem uh, using the generalized compressibility chart. All right, I think I will stop here, and this chapter is very important from exam point of view. uh, for exam 1, you get many questions from this chapter. Thank you very much.